Modern autonomous driving systems integrate tens of heterogeneous processors, high-bandwidth networks, and millions of lines of code. Proving the functional safety of these software-defined vehicles under ISO26262 requires mapping every possible interaction. But extreme architectural density means a single point of failure can easily cascade through the entire autonomous system. The most persistent threat in this environment is a Dependent Failure Initiator, or DFI. This occurs when multiple independent, safety-critical functions rely on a hidden shared resource, like a single memory bus or power unit. A fault in that shared resource causes a common cause failure, simultaneously disabling systems that were designed to operate redundantly. Traditional model-based systems engineering attempted to track these dependencies using SysML version 1. However, that language modeled structures as visual representations without underlying formal mathematical semantics. It drew pictures of systems, but it could not calculate their behaviors. Because the architectural models could not be mathematically evaluated, system design and safety analysis split into separate domains. Engineering teams built system structures in dedicated drawing tools, while reliability teams tracked failure mode and effects analysis in entirely disconnected spreadsheets. Relying on disconnected static diagrams to manage dynamic complexity ensures that critical failure pathways remain invisible. By the time expensive physical vehicle testing reveals a dependent failure, the hardware architecture is already permanently locked in. SysML version 2 replaces the drawing board with a compiler. Built on a logical foundation called the Kernel Modeling Language, or KerML, it translates architectural geometry into executable code. Every component and connection now carries strict mathematical and logical meaning. Engineers can seamlessly alternate between textual syntax and GraphQL syntax. This bidirectional environment ensures that the visual representation remains strictly tethered to its logical definition, allowing for the automated detection of structural inconsistencies. The language also introduces standardized REST APIs. Instead of trapping model data inside proprietary desktop applications, the architecture lives on enterprise servers, where it can plug directly into continuous integration and continuous deployment pipelines. Because the model is accessible via API and built on logic, safety requirements evolve from static spreadsheet checklists into automated runtime queries. The intelligent architecture actively interrogates itself for hidden vulnerabilities and structural flaws, entirely during the early design phase. Functional safety is no longer an isolated, reactive documentation task. SysML version 2 compiles the architecture mathematically, allowing engineers to identify and block dependent failures before a single physical component is manufactured. To see how physical dependencies are captured, we look at the SysML version 2 authoring environment. The workspace operates in two synchronized panes, code on one side and the graphical architecture on the other. Typing part definition commands for a power management unit and shared memory generates geometric blocks. Linking them with connect syntax establishes a semantic bond, mapping the energy exchange between interfaces. We introduce two processing cores, routing both to the same power supply node. This intersection is stored as formalized metadata. If a search current hits, the system knows exactly which ports carry the fault. The physical wiring is locked into code. By defining dependencies strictly through syntax, the architecture is permanently formatted for automated safety analysis. Physical wiring is ISO26262, but software dependencies are often hidden. Autonomous systems run dozens of tasks concurrently, and competing for memory access or CPU time creates dynamic logical coupling. This timeline illustrates a CPU scheduler. An A-cell-D steering task and a non-critical logging task queue in the same 10-millisecond window. We apply a constraint block, overlaying an algebraic equation to map worst-case execution times. Assigning a 5-millisecond execution time to steering and 7 to logging totals 12 milliseconds, pushing the critical task past the deadline. The console calculates this overrun, automatically generating a failure flag at the architectural level. The code inherently understands the limits of time and processing power. It catches and flags dynamic interferences before the engineering team even begins writing software or running simulations. Detecting structural faults is only half the equation. Engineers also need to track failure probabilities. That requires moving reliability metrics out of static spreadsheets and into the model itself. The Object Management Group developed RAML, the Risk Analysis and Assessment Modeling Language. It provides a standardized framework to directly bind failure mode data to system definitions. Using RAML, engineers attach a safety event profile annotation to a brake caliper block. Expanding it reveals variables, the exact failure mode, a severity score of 9, and the precise likelihood of failure. This establishes bidirectional traceability. Updating the brake caliper's likelihood of failure sends a mathematical ripple up the architectural tree, instantly recalculating the top event probability for the entire vehicle. Embedding this metadata turns the design into a living safety database. Localized hardware changes immediately impact system-wide risk assessments without a single spreadsheet transfer. SysML version 2 maximizes utility by exposing model data through standardized REST APIs, integrating the architecture directly into high-speed enterprise cloud environments. When an engineer commits a new architectural code change to the repository, it triggers an automated Python script within the team's continuous integration pipeline. The script calls API endpoints to recursively parse elements, flattening the system graph into a machine-readable JSON payload. An AI agent scans this graph topology, parsing thousands of connections to highlight a structural anomaly. The scanner identifies a dependent failure initiator. A previous commit stealthily routed both the primary steering module and backup braking module through the exact same CAN network switch, converging on a single red node. Once detected, the API executes an automated post command. It reaches back into the model server and injects a validation failure requirement directly onto the offending component, forcing the engineer to redesign the network path. Pairing REST API access with formal modeling creates an unblinking automated guardian. It audits massive, complex architectural changes instantaneously, blocking critical safety flaws from ever reaching the software development phase. As vehicles approach higher levels of autonomy, tracking dependencies across mixed-criticality systems becomes incredibly difficult. Top-tier safety functions constantly overlap with non-critical infotainment and telematics hardware. To manage this density, SysML version 2 utilizes a viewpoint rendering feature. This command allows engineers to construct specific queries that aggressively filter out architectural noise. We can program a visual filter that specifically extracts the cross-connections between the lowest safety-rated QM components and the highest safety-rated ASIL-D components. It fades out the irrelevant data, exposing the exact paths where low-level faults might jump into critical systems. Isolating these paths explicitly defines the boundaries where freedom from interference must be proven. The design team addresses these exposed bridges by placing a logical firewall, memory protection unit, or data gateway directly into the architecture. Targeted algorithmic rendering forces hidden architectural vulnerabilities to the surface, neutralizing human oversight and guaranteeing strict isolation between critical and non-critical domains. To optimize hardware costs, engineers frequently rely on ASIL decomposition. This technique splits a top-tier safety requirement across multiple redundant channels. However, the ISO26262 standard mandates that these duplicate channels must maintain absolute architectural independence from each other. To prove this independence, we embed a runtime verification query directly into the system model. It utilizes a depth-first search algorithm to crawl downward through the underlying hierarchy of every component. The search algorithm actively traces the subsystem roots of what are supposedly independent sensor channels. It travels down the physical routing, checking power supplies, data buses, and clock lines. During the crawl, the algorithm detects that both parallel channels trace back to the exact same clock generator component. The independence requirement fails, triggering a terminal rejection that instantly halts the system build. SysML version 2 transitions autonomous vehicle engineering away from reactive diagramming. It forces the design to survive rigorous, proactive mathematical scrutiny before integration begins. By compiling functional safety directly into the architecture's foundational code, engineering teams secure the extreme reliability required for the future of mobility, neutralizing the inevitability of complex systemic failure.